All right. Well, we have three attack types that we're going to be going over. First, we have reconnaissance, access, and then we're going to go over denial of service. Reconnaissance is mostly with the aim to gather information about the network. It is not about the user, the threat actor, trying to damage the network. It's more so gathering sensitive information like passwords, usernames, IDs, and possible parts of down in the firewall. With access now, the threat actor can actually use that information that they've gathered to gain unauthorized permissions to change and alter their addressing so that they'll be able to be recognized as a valid user of the network. With denial of service, the threat actor is interacting with the network with the aim to disrupt a specific service. Now, with denial of service, this could actually overlap with other types of attacks because the user can not only send out messages to overwhelm the server, they can also convince other valid clients to do the same and overuse the resources so that the valid users with no idea that this is happening disrupt their own service. Okay, let's move on. Okay, going back to denial of service. This could happen for a client on the network if they were to access a corrupted file or open a fraudulent email or a website that upon downloading or viewing installs a program that responds to the threat actor to do a certain action. Now, the difference between viruses and worms is that worms always active. Viruses, however, are executed upon the user performing an action. Now, viruses can be initiated by the user opening a certain application and typing something in. Versus worms, even if you were to delete the directory that it was in, it can still infect other files and directories on your file system, resulting in the malware still being there despite that the original directory it was in no longer being there. Okay. Some other types of malware would include Trojan horses and spyware. Now, a Trojan horse is a program that simulates another program or similar application to allow for the threat to be installed without detection. It allows the threat actor to alter other host programs that could change the behavior of the machine. Now, with spyware, the program is actually capturing the data from the user session. This could include passwords, account ID, and sensitive footage. Okay, and let's go over some different network attacks. Let's go over reconnaissance attacks. With reconnaissance attacks, like I said, you are not initiating the attack primarily to stop service, but to gain information. You can use eavesdropping packet sniffers, which prevent the user from being able to detect that the threat actor is actually taking up their information. To to prevent this from occurring, the user can actually request for some type of encryption to be placed upon their messages between the client and the server that they're requesting information from and communicating with. Okay, let's move on. Next is access attacks. With access attacks, you have your IP spoofing, your session hijacking, your rerouting, and with these three, IP spoofing means that the threat actor was actually able to change their IP address so that it is the same as an actual user on the system. This is how a threat actor can actually initiate a denial of service by spoofing their address to a valid user and sending out a ping to all users on the network. That way, when the devices send out their reply, they're directing it to some poor host who's just had their address spoofed and overloads that connection, so the user no longer has service to the server. With session hijacking, the threat actor is actually taking over the user's session. So the threat actor is able to control the machine of the user. With rerouting, the threat actor is able to impersonate the server and change the specific server that the user is communicating with that is actually owned or controlled by the threat actor. To prevent this, we can go ahead and use passwords to authenticate the user before we confirm their IP address for messaging. Okay, let's go ahead and move on. With social engineering attacks, they use normal gestures and verbiage to convince other users to click on them or to download them, like emails, or possibly it being in a data center and allowing a user that would not normally have access to special equipment to that user. Okay, moving on. Okay, our first bit is denial of service. Now, denial of service can be split off into two types. The difference between these can be simulated with a cafeteria. Imagine the cafeteria on a normal day with a steady stream of students, personnel, and goods moving around the place. An example of a sin flood would be if hundreds of UNCC students came to eat at our cafeteria at the same time and made orders for food and then quickly left before the orders were fulfilled. The cafeteria would stop, allowing students in so they can handle the large order, which would mean that the actual students who could no longer have access to the legitimate service. A DHCP starvation would be if the UNCC students were able to encourage so many orders to be fulfilled that the cafeteria ran out of food. Stepping away from the food examples, malignant frames could be DOS attacks that involve the formatting of the threat actors framed to stall the server's operations. Okay, moving on. Okay, now we're talking about some common IP and ICP attacks. We have ICP echo request, ping reply, amplification and reflection, address spoofing, man in the middle attacks, and session hijacking. Now, IP does not validate whether validity of the source address of incoming packets is actually the packet that should be coming. ICMP attacks echo and ping messages to check for network structure used in ICMP floods, and they're used to alter host routing tables. Now, with reconnaissance and scanning, it is used to check the state of the firewall with ICMP Discover. With amplification and replication attacks, they attempt to prevent users from accessing services using denial of service attacks or distributed denial of service attacks. They can be used to discover the addresses as part of the network database and which of the registered addresses are active, identify the host OS, and scan for vulnerabilities in their firewall. With address spoofing, you can have blind or non-blind spoofing by changing the source IP address. With man in the middle, the threat actor places themselves between the source and destination to monitor and control communication. All right, moving on, we have some more echo request and reply, unreachable, ICMP mass reply, ICMP redirects, and ICMP router discovery. With ICMP echo request and ping reply, that is used for host verification and denial of service. With ICMP unreachable, that is used to perform network recon and scanning attacks. Next, mass reply is used to map the internal IP network. ICMP redirects is used to convince the host to send all traffic through a compromised device being monitored by the threat actor. Router discovery attacks alter the default routes in a host routing table to redirect to compromised devices. For example, low orbit ion cannon can connect the client to server to remotely control the client and spread zombies. And zombies are clients who unknowingly spread to each other a type of malware that the threat actor can use to control those machines and to propagate a DDoS. Okay, and let's move on to the next slide. We have amplification and reflection attacks. They're used to create a denial of service attack. Amplification is when forwarded ICMP echo requests are broadcasted to all hosts, but the header isn't addressing, then change source information to target another host. Source IP addresses and reflection is where valid hosts send back valid replies to the target source address, which use up connections bandwidth, stops the targeted host from accessing any resource for the duration of the task. Okay, next we have address spoofing attacks. Blind attacks are where the threat actor cannot see traffic between the host and the target. Now, this does not mean that the threat actor is doing a better thing than non-blind spoofing attacks, which is the threat actor actually trying to hijack the session through reconnaissance of the reply packets. Because with non-blind spoofing attacks, the threat actor is testing the network, versus blind spoofing attacks, the threat actor is cutting off parts of the network. Now, testing with the tests, the threat actor can actually not only possibly a commission for a DOS attack, they can actually share this with others and have them also perpetrate a DOS attack against a certain organization. With non-blind spoofing attacks, it is just used to check the firewall and the sequence number prediction value. And it can be used to assign the threat actor as a valid user in the network. All right. Okay. In your TCP segment header, you have values that tell the frame what message it needs to send to another host to continue a connection. So you have urge, ACK, push, rest, send, and fin. These correspond to mean urgent acknowledgements must rest to push synchronized finishes. Urgent means that the frame is significant. Acknowledgement means that the frame has been received. Push means that the frame must be forwarded. Rest means that the connection needs to be reset. Synchronized means that we need to change the order of the frames. And fin means that this is the last frame. Okay, moving on. Now there are three main TCP services offered. It offers reliable delivery. So if a client receives a segment, it will send out a frame with the acknowledgement value in the header and resend frames if it does not. Or it has flow control, which means that it is able to respond with an acknowledgement frame to multiple hosts at the same time. Then it has stateful communication, which means that it engages in a three-way handshake to ensure that the host is ready to connect before sending anything. Now, a three-way handshake is if we were both hosts, would be if I sent out a synchronous frame to you, I'm asking you if you are ready to connect with me. Now, then you would send a synchronous acknowledgement frame to me to tell me that you are ready to accept the connection. Now, when I receive that, I'm going to send you back an acknowledgement to pretty much say that, oh, we have both agreed on the connection, let's go. And so we can open up a new session, a connection session with a send ACK to you. Now moving on, we have some TCP attacks. Let's start with TCP send flood attacks. They are designed to overwhelm the target with half-open TCP connections that were made by the threat actor randomly spoofing addresses to send frames, but not to acknowledgements, so that the target must use up its memory and addresses to keep it open. Now, with TCP reset attacks, termination is done without having to acknowledge a fin frame, but the threat actor can send a frame from a spoof address to forcibly shut down the connection. Now, with TCP hijacking attacks, the spoofed address of a host on the network, we try and predict the synchronized number flag of the frame being received, and then send an acknowledgement back to the destination so that we can send off data from the authenticated host. Okay, moving on. Then we have UDP attacks. UDP is connectionless, which means that it's very fast because it does not require authentication or encryption by default. This means that anyone with access to the network can view and modify the contents and destination of incoming packets. In a UDP attack, network resources are consumed by the continuously sending UDP packets to the target server. The server will then look through all its ports for the source of the packet. For each closed port, an ICMP port unreachable message is sent. If this goes on for long enough, the busy segment traffic on server will lower the bandwidth and restrict access to verifiable hosts. Okay, moving on. ARP vulnerabilities. Upon boot up, a device connected to the network will broadcast its IP address and MAC address for all other hosts to be able to add it to their ARP table. There is no check to confirm if the address being claimed is verifiable, which threat actors can use to change the default gateway that the users use to communicate traffic to the compromised device, to allow the threat actor to be able to monitor and control the traffic and identify vulnerabilities in the network's firewall. With ARP poisoning, it is where a compromised device connects to the network to send spoofed ARP replies to a device to change their routing table. Altering the valid entry to match the compromised device can allow the threat actor to be able to alter incoming data, which is called active poisoning, or record confidential information being directed to the valid host, which is passive poisoning. Alongside this are spoofed ARP entries. The threat actor can change their address to alter the ARP entry to match a part of a valid entry and will be able to view information in incoming frames, therefore becoming a valid device. All right. Next, we have DNS attacks. Now, with DNS attacks, let's start with open resolver attacks. Now, open resolver attacks, they answer queries from the clients outside the administrative domain. The threat actor, can send spoofed record resources to DNS resolvers to use a false name server that redirects users to alternate sites. It can send DNS messages to the server with a spoofed source address for open resolver to respond with queries to the target to increase the volume of the DDoS attack. This can cause services of the open resolver to be stopped from being received by valid hosts by consuming resources using a DDoS attack. Now, with stealth attacks, they are primarily used to hide the attacker's identity during an attack of another type. You have fast faults, which periodically changes the attacker's hijack session between many compromised DNS hosts to avoid the source of the malware from being detected. You have domain IP flux, which rapidly changes the host name to IP address mappings and the attacker's name server to increase the difficulty of pinpointing the attacker's real address. You have domain generation algorithms. They're used to randomly generate domain names that redirects connections to join the threat actor's pool of compromised hosts in the compromised network. And then you have DNS tunneling. It is used to place non-DNS traffic within DNS traffic to sneak confidential information to pass any check for the attacker's authorization to change the content type of their queries. Data from compromised devices are split into chunks among a series of DNS queries as part of their domain name label. These will be forwarded by the ISP's recursive DNS servers to the threat actor's name servers, since there would not be a reply from any of the uncompromised servers. Upon receipt, the query messages are compiled till all queries have been sent and replies with its own commands for the devices to enact with each query it sends. The process is repeated till a compromised device has encapsulated and compiled the messages into commands for the client to do. Using a filter to check the labels and contents of unusual queries can help to prevent the continuation of information being tunneled to and from compromised devices. This DNS tunneling is like a wolf in sheep's clothing being herded around a herd of sheep. Now, it can communicate with its pack, but it still can go back and forth stealing sheep from the main herd without anyone knowing. So let's keep going. Our next is DHC spoofing and DORA. DORA is the same. The client broadcasts DHCP discovery messages. All DHCP servers send an offer, but the client replies that it has accepted the first offer. If the reply mentions that the actor server, then only that server will send back an acknowledgement with the invalid information to that host. Then the user is going to end up speaking or communicating with the threat actors servers instead of the valid servers for that network. Okay, let's keep going. Next, we have the CIA triad, which consists of confidentiality, integrity, and availability. Confidentiality, it means that only authorized users should be able to access services. It is ensured by using symmetric encryption algorithms like AES and SEAL, which are both very secure due to their higher range of encryption key lengths. Now, with integrity, it means that the hash that a segment of data was assigned upon transport should be the same upon receipt. The hashed message authentication code guarantees the integrity of a hash value. The most common are MD5 and SHA. Now, with availability, it means that authorized users should always have access to important resources and data 24/7. This is done by using redundant services with multiple ISPs, establishing multiple gateways, and redundant links. Okay. Next, we have defense in depth and the layered approach. With defense in depth approach, it is a combination of security devices and services that work in tandem to monitor traffic for suspiciously long packets. It filters out these suspicious messages from regular traffic, encrypts outgoing traffic, and decrypts it upon reaching its destination with encryption keys used for the user's authentication. Packets are dropped before they can be decrypted. If the user cannot provide proper authentication or messages arrive from sources that have been learned as hosting malware. Securing internal traffic is good, but it is more important to ensure that traffic is not compromised as confidential data about all connected networks could get out. Okay, now moving on. What are firewalls? They are normally on the egress interface that marks the start of the local loop to allow for all inter-network traffic to flow through it and filter out traffic based on access lists. Now, some good things about it is that they are resistant to network attacks, which does not allow outside clients that have not been authorized to access in-network services and resources. They are good at dividing network access management across multiple firewalls, which allows for less complex network security. But it's not always great, because with misconfigured firewalls, they can act as a single point of failure for the whole network and lead to downtime. Higher resource utilization for monitoring, filtering traffic can lower network performance. And firewalls may not be able to detect unauthorized edits to data traffic that has been encapsulated and spoofed. Okay. All right, moving to the next one, we have IPS and IDS. Now, IPS is more scalable than IDS because it is able to filter traffic based on a set of access policies. They can be configured on Cisco routers as an additional service or as a specialized service on a dedicated device or as a network module for a switch or a router. IPS interprets incoming traffic and compares it with known threats and access policies. The IPS requests that its log message of any incident that has occurred be sent to the management console. Packets are dropped if the console determines that the filtered packet awaiting a decision should be dropped. Okay. Next, we have content security appliances. They are separate content security appliances for email and web browsing. For email security appliances, they monitor simple mail transfer protocol messages and updates its database of known threats every about 3 to 5 minutes. Cisco Web security appliances focus more on how users access the internet and can blacklist sites and services or traffic on a network. WSA compares the source of a server reply to a query that was forwarded over by the firewall. Packets of blacklisted sites are dropped if the query is in violation of access policies. Okay, next, we have data integrity. It means that the hash that a segment of data was assigned upon transport should be the same upon receipt. The hash message authentication code guarantees that the integrity of a hash value stays the same throughout the entire communication. The most common are MD5 and SHA. Next, okay. The hash message authentication codes provide an additional authentication key on a message to ensure its integrity. Only the sender and the destination should know this keyed hash combination. First, you have to create the HMAC of value by calculating the fixed length key for the message and assigning it a value, and then the frame is sent. Now, upon receipt by the destination, the destination client has to verify the HMAC value upon receipt to check with its known secret key and compare it with the assigned value. If they match, then the contents are decrypted and read for the user, but if not, the frame is discarded. All right, last slide, we talk about data confidentiality and the difference between symmetric encryption and asymmetric encryption. Now, symmetric encryption uses the same key to encrypt and decrypt data. And key lengths can range between 40 to 256 bits. They include DAS, 3DS, AES, and SEAL. AES is the most common. It can offer 3 different key lengths, 192, 128, and 256. And it is both more secure and efficient than DES and 3DS. SEAL encrypts data continuously using a 160-bit key, and it's the most secure out of the symmetric encryption algorithms. Now, with a symmetric encryption, Diffie-Hellman, which is 512 to 4096, is used for exchanging data using VPNs between devices. When SSH data is exchanged and when data is exchanged using an SSL or TLS VPN. It assigns a secret key on both the sender and destination before they communicate. Now, with Rivest, Shamir, and Alderman encryption algorithms, or RSAs, they are normally 512 bits to 2048 bits, and they are a public key encryption that is used for very large numbers and is used for signing and encryption. Now, with digital signature algorithms, which are 512 to 1024 bits, they are also public key algorithms, much like RSAs, and are seen by users on the network. They have a very fast creation, but very slow verification. With elliptic curve cryptography, which uses 224 bits, it is a technique to allow decryption between devices using different algorithms. Now that is the last slide. Thank you for coming and listening to our presentation today. I hope you enjoy the rest of your day. Thank you for coming.